Science is a way to answer questions about the world. It is not a set of facts, but a method for finding out what is true. The method asks for observation, for testing, for careful thinking. It began a long time ago, with people who tried to explain why rain falls or why a stone rolls down a hill. One of the earliest thinkers was Aristotle. He lived in ancient Greece and tried to put nature into categories. He said that the world can be understood by looking at its parts and how they work together. He wrote, "Nature does nothing in vain." That short line shows his belief that the world follows rules that can be discovered. Centuries later, a man named Francis Bacon wrote about a new way to learn. He lived in England in the early 1600s. He argued that people should collect many facts, then test ideas by experiments. He wrote, "Knowledge is power." Bacon's words helped turn curiosity into a disciplined practice. His ideas were the seed of what later became the scientific method. The scientific method is a step-by-step plan. First, a question is asked. Next, a hypothesis, or a guess, is made. Then an experiment is set up to see if the guess works. Finally, the results are looked at and shared. If the results match the guess, the idea is stronger. If they do not match, the guess is changed or dropped. The basic idea of science can be shown with everyday life. Imagine a person who wants to bake a new cake. The recipe says to add 1 cup of sugar, but the baker thinks 2 cups might make it sweeter. The baker tries the cake with 1 cup, then with 2 cups, and tastes each one. By comparing the results, the baker learns which amount works best. This is science in a kitchen. The baker asked a question, made a guess, tested it, and learned from the outcome. Another simple example is checking how long a phone battery lasts. A person might think the battery will last 8 hours after a full charge. The person charges the phone, uses it normally, and watches the clock until the battery dies. If the phone lasts only 6 hours, the person notes the difference. The next day, the person may close some apps and try again. By changing the way the phone is used, the person learns what makes the battery last longer. This is the same pattern that scientists follow. Ask, guess, test, learn. These 2 examples show that science is not only for labs. It is a habit of mind. It can be used to fix a broken bike, to choose the best route to work, or to decide which plant needs the most water. In each case, a person looks at what is happening, makes a small change, watches the result, and decides what to do next. Some people argue that science is not needed. One common claim is that personal belief can replace testing. A person might say, "I feel that this medicine works, so I do not need a trial." That view trusts feelings over evidence. The problem with this view is that feelings can be wrong. A person can feel better after taking a sugar pill, even though the pill has no real effect. Without testing, there is no way to know if the medicine truly helps. Another claim is that tradition alone is enough. Some say, "Our ancestors have used this herb for centuries, so it must be safe." Tradition can hold useful knowledge, but it can also keep old mistakes. In the past, people used lead for pipes because it seemed strong. It took many years of testing to discover that lead harms health. When tradition is trusted without question, harmful ideas can stay hidden. History shows how science grew by questioning old ways. In medieval Europe, alchemy tried to turn base metals into gold. Alchemists mixed strange substances and recorded their work. but they did not have a clear way to test if they succeeded. Over time, a few thinkers began to separate alchemy from what we now call chemistry. One of them was Robert Boyle. He insisted that experiments must be repeatable, meaning anyone could do the same test and get the same result. Boyle's approach turned the mysterious work of alchemy into a reliable study of matter. This shift from alchemy to chemistry is a clear example of how testing replaced belief. A second historical story comes from the 17th century. Before that time, many scholars relied on ancient texts and on the word of authority. When Galileo looked at the moons of Jupiter through a telescope, he found that not everything moved around the Earth. He wrote, "And yet it moves." His observation contradicted the long-held belief that the Earth was the center of the universe. Galileo's work showed that looking directly at nature and testing ideas with instruments could overturn old ideas. The rise of the scientific method in this era gave people a new tool to check the world, not just trust old books. Modern science still follows the same steps. In medicine, doctors run clinical trials to see if a new drug works better than a placebo. In climate science, researchers collect temperature data from many places, then use computers to see if the patterns match the idea of a warming planet. In technology, engineers test different materials to make phones that are stronger and lighter. All of these fields use the same basic pattern that Aristotle and Bacon first described. Science also has a modern interpretation that adds a social layer. Some philosophers say that science is a community activity. A scientist writes a paper, other scientists read it, try the experiment, and either agree or point out problems. This back and forth helps keep the work honest. It also means that science is not just about one person's idea, but about many people checking each other's work. This community check is why a single mistake does not usually stay hidden for long. An analogy can help picture this process. Think of science as a garden. The gardener plants a seed, watches it grow, and notes how much water, sunlight, and soil it needs. If the seed does not grow, the gardener changes one thing at a time. More water, less sun, richer soil. Over time, the gardener learns the best way to grow a healthy plant. In the same way, scientists plant a hypothesis, test it, and adjust based on what they see. The garden only thrives when the gardener pays attention and adapts. Another analogy is that of a detective solving a mystery. A detective gathers clues, forms a theory about what happened, then looks for more evidence to confirm or reject the theory. If new clues do not fit, the detective changes the theory. Science works the same way. It looks for clues in nature, builds a story, and then checks if the story fits the clues. The story that fits best becomes the accepted explanation, until new clues force a change. The everyday examples, the historical anecdotes, and the analogies all point to the same idea. Science is a way of asking and answering. It is not a set of rigid rules that never change. It is a flexible habit that helps people move from guesswork to reliable knowledge. When a person tests a new recipe, they are doing the same kind of work that a chemist does in a lab. When a person checks a phone battery, they are using the same method that an engineer uses to design a better battery. The power of science lies in its ability to correct itself. When a test shows that a belief is wrong, the belief can be dropped. When a new test shows a better way, the old way can be improved. This self-correction is why science has produced vaccines, computers, and space travel. It is also why science can be trusted more than personal belief or tradition alone. A final quote from Francis Bacon sums up the spirit of this method. He wrote, "If a man will begin with certainties, he shall end in doubts. But if he will be guided by the experience of the senses, he shall find truth." This line reminds the listener that certainty without testing leads to doubt, while careful observation and experiment lead to truth. In sum, science is a quest that began with thinkers like Aristotle, grew with the ideas of Francis Bacon, and continues to shape daily life. It asks simple questions, makes simple guesses, tests them, and learns from the results. It can be seen in a kitchen, in a phone, in a laboratory, and in the sky. It survives because it does not rely on belief alone, nor on tradition alone, but on evidence that can be checked by anyone. The next time a person wonders why a plant wilts or why a video game crashes, the scientific habit offers a clear path. Observe, guess, test, and learn. This path has turned myths into facts and curiosity into progress. Observation and experiment sit at the heart of how science builds ideas. In the story of science, watching the world and testing ideas work together like two hands that shape a piece of clay. The story begins long before modern labs. It begins with a man who lifted his eyes to the night sky and built a simple tube to see farther. That man was Galileo Galilei. He pointed his telescope at the moon and saw mountains and valleys. He watched Jupiter and counted 4 bright spots that moved around the planet. He wrote, "The heavens are not immutable, but changeable like the earth." That simple observation changed the way people thought about the universe. Galileo did not stop at looking. He built experiments to test his ideas. He let a ball roll down an inclined plane and measured how fast it went. He wrote, "Measure what can be measured, and make measurable what cannot be measured." He used a ruler and a balance. He repeated the roll many times. Each time he recorded the time with a water clock. He compared the numbers. He saw a pattern. The pattern told him that the speed of a falling object grows in a steady way. That pattern became a law that still guides physics today. A few centuries later, another curious mind turned observation into experiment. Michael Faraday loved to watch sparks jump between wires. He built a coil of copper wire and moved a magnet through it. He watched a tiny electric current appear in the coil. He wrote, "Nothing is too wonderful to be true." He repeated the motion again and again. Each time the coil lit a small lamp. He measured how fast the current grew when the magnet moved faster. He turned the idea of invisible forces into something that could be seen, heard, and measured. His work laid the foundation for electric generators and motors that power modern life. These two stories show a pattern. First, a scientist watches a natural phenomenon. Then the scientist designs a test that can be repeated. The test produces numbers that can be compared. The numbers tell whether the idea matches reality. If the numbers do not match, the idea is changed or dropped. This cycle of watching and testing is what makes science reliable. A simple everyday example can illustrate the same process. Imagine a garden where a plant leans toward a bright window. One can watch the plant each day. The plant's leaves turn a little more toward the light. That is observation. To test why the plant does this, a person can cover half the window with a dark cloth. Then the plant will turn toward the open side. By measuring the angle of the leaves each day, the person can see a clear pattern. The pattern shows that light guides growth. The test confirms the observation. This small garden experiment mirrors the work of Galileo and Faraday, only on a smaller scale. Another easy example comes from a bike ride. A rider can watch how long it takes to travel from home to a park on a straight road. The rider notes the time with a phone. Then the rider tries a different route that goes over a hill. The rider measures the new time. The rider may find that the hill route takes longer even though the distance is shorter. By comparing the two times, the rider learns that slope matters as much as distance. This simple test shows how experiment can reveal hidden factors that observation alone might miss. These examples show that observation and experiment are not separate tricks. They are two sides of the same coin. Observation points out a puzzle. Experiment tries to solve the puzzle. The solution becomes part of a larger picture that scientists call a theory. The role of observation and experiment has been debated. Some people claim that intuition alone can give the right answer. They say that a scientist's gut feeling can guide discovery without the need for careful testing. This view appears in stories about great inventors who just knew how something would work. The claim sounds appealing because it makes the creative mind seem magical. However, history offers many cases where intuition led to a dead end. When Galileo first pointed his telescope at the moon, his intuition told him that the moon might be smooth. He watched the craters and realized his intuition was wrong. He changed his view because the observation forced him to revise his guess. Without the test, the false intuition would have stayed. A second criticism says that experiments can be biased. The claim is that a scientist may see what they want to see, or set up a test that favors a certain outcome. This worry is real. In the early 20th century, some psychologists set up experiments that only measured people who already agreed with their ideas. The results then looked convincing, but the method was flawed. The criticism reminds us that experiments need careful design. They need control groups, blind procedures, and repeatability. When Faraday built his electric coil, he took great care to repeat the motion many times and to check that the current appeared each time. He did not rely on a single flash of light. By repeating the test, he reduced the chance that his own hopes colored the result. Modern science still faces these challenges. Today, scientists use computers to run simulations that act like virtual experiments. They watch the output of the simulation and compare it with real data. They also use large data sets from telescopes, particle colliders, and DNA sequences. In each case, the process still starts with observation. The observation points to a pattern or a mystery. Then a test is designed, often with many variables, to see if the pattern holds under different conditions. The test must be repeatable by other labs around the world. If the results match, the idea gains strength. If not, the idea is revised. A modern interpretation of observation and experiment comes from the idea of model-based science. In this view, a scientist builds a simple model, a picture of how they think the world works. The model predicts what should happen. Then the scientist watches the world and runs experiments to see if the predictions match. If the predictions fail, the model is changed. This loop is the engine of progress. It is the same engine that Galileo used when he watched the moons of Jupiter and then built a model of a solar system that placed Jupiter at the center. It is the same engine that Faraday used when he watched magnetic fields and then built a model of electromagnetic induction. Real-world applications of this method are everywhere. In medicine, doctors watch patients' symptoms and then test a new drug in a controlled trial. They measure how many patients improve compared to a placebo. The trial is the experiment that tells whether the observation about the disease can be treated with the new drug. In agriculture, farmers watch how crops grow under different fertilizers. They test each fertilizer on a separate plot of land. By measuring yield, they find which fertilizer works best. The observation of plant health leads to an experiment that guides future practice. Another example comes from climate science. Scientists watch the temperature of the oceans rise over decades. They then test the idea that carbon dioxide causes warming by running computer experiments that add CO2 to a virtual atmosphere. The models predict a rise in temperature that matches the observed data. The match gives confidence that the idea is correct. The observation of warming and the experiment of modeling together shape policy decisions about energy use. Analogies help to make these ideas clear. Think of a detective solving a mystery. The detective first looks at the scene. This is observation. The detective then gathers clues and runs tests, like dusting for fingerprints or checking alibis. Each test tells whether a suspect fits the story. The detective repeats the steps until the picture becomes clear. Science works the same way. Observation is the crime scene, experiment is the test that narrows down the possibilities. A historical anecdote about Galileo's telescope trials shows how careful testing can overturn long-held beliefs. When Galileo first pointed his telescope at the night sky, he expected to see perfect circles around planets, as the ancient philosophers claimed the heavens were flawless. Instead, he saw craters on the moon and spots on Jupiter. He recorded his sketches and showed them to friends. Some friends dismissed the sketches as tricks of the lens. Galileo then repeated the observation on many nights, using different lenses, and each time the same features appeared. The repeated tests convinced even his skeptics that the heavens were not perfect. This story illustrates that a single observation can be misleading, but repeated experiments can settle the dispute. A second anecdote about Faraday's electric experiments shows the power of simple tools. Faraday worked in a small laboratory with a coil of wire, a magnet, and a piece of glass. He moved the magnet back and forth and watched a tiny spark jump across a gap. He measured the spark's strength with a galvanometer, a device that shows electric current. He tried moving the magnet faster, slower, and even rotating it. Each change gave a different reading on the galvanometer. By plotting the speed of the magnet against the current, Faraday discovered a clear relationship. He turned this relationship into the law of electromagnetic induction, which later allowed engineers to build generators that power cities. The story shows that careful observation combined with systematic testing can turn a simple spark into a technology that lights up the world. Quotes from the original thinkers add flavor to the narrative. Galileo wrote in a letter to a friend, "The book of nature is written in the language of mathematics." He meant that numbers and measurements are the key to understanding what is seen. Faraday wrote in a notebook, "Give me a place to stand, and I shall move the world." He was speaking about the force that a moving magnet can exert on a wire. Both quotes point to the same idea. Observation becomes powerful when it can be expressed in measurable terms. The role of observation and experiment also appears in everyday decisions. A child watches a ball roll down a ramp and learns that steeper ramps make the ball go faster. The child then builds a ramp at home and tests different angles. By measuring how far the ball travels, the child learns a simple rule about slope and speed. This personal experiment mirrors the work of scientists who study motion. It shows that the method is natural to human thinking, even before formal education. In the classroom, teachers use similar steps. They show a video of a chemical reaction that changes color. Students then mix the same chemicals in a beaker and watch the color change themselves. They record the time it takes for the color to appear. By comparing their notes with the video, they see how observation and experiment reinforce each other. The lesson becomes more than a fact. It becomes a practice of how knowledge is built. Science also learns from failed experiments. When an experiment does not match the observation, the result is not a loss but a clue. In the early 1900s, physicists tried to measure the speed of light in different directions, expecting to find a change due to the motion of Earth through a supposed ether. The famous Michelson-Morley experiment found no change. The observation that the speed was the same in every direction puzzled scientists. This negative result forced a new idea: that space does not need an ether. Albert Einstein later used this result as a stepping stone for his theory of relativity. The story shows that even a null result, an experiment that seems to show nothing, can reshape science. Another case of a surprising experiment involves the double-slit experiment in physics. When light passes through two narrow openings, it creates an interference pattern on a screen. This pattern suggests that light behaves like a wave. But when scientists send one photon at a time, the pattern still appears after many photons have hit the screen. The observation that a single particle can create a wave pattern challenged the idea that particles are just tiny balls. The experiment forced a new model of quantum mechanics. This example shows how a simple observation combined with a clever experiment can overturn long-standing ideas about the nature of reality. The modern world relies on observation and experiment in many fields. In technology, engineers watch how a new material reacts to heat. They then test the material by heating it in a furnace and measuring its strength. The data guides the design of airplane wings that can withstand high temperatures. In finance, the story of science often feels like a long road made of many small steps. One step is called a law. Another step is called a theory. Both are important, but they are not the same. A law tells what happens in a certain situation. A theory tells why it happens. To see the difference, it helps to look at two famous people, Isaac Newton and Charles Darwin. Newton lived in the 1600s. He studied how objects fall and how planets move. He wrote a short rule that says every object pulls on every other object with a force that depends on their masses and the distance between them. That rule is now called the law of universal gravitation. In simple words, the law says that if two objects are close, they pull harder. If they are far, they pull weaker. The law does not say why the pull exists, only how strong it is and how it changes with distance. Newton also wrote a longer explanation called the theory of motion. The theory says that objects keep moving in a straight line unless a force makes them change direction. The theory also explains why the law of gravitation works. In the words of Newton himself, the motions of the heavens are caused by the same forces as those on Earth. That sentence shows how a theory can connect many facts under one idea. Darwin lived 100 years later. He traveled the world and watched many animals. He noticed that some birds travel far each year. He called that pattern migration. He also saw that some animals look different in different places. From those observations, he built a big idea called the theory of evolution by natural selection. The theory says that living things change over time, because the ones that are best at surviving leave more offspring. The theory also gives a reason for the rule that birds migrate. It says that birds move to places where food is easier to find, and those that do not move may not survive. Darwin wrote, "There is grandeur in this view of life, with its several powers, having been originally breathed into a few forms or into one, and that, whilst this planet has gone round the sun for billions of years, it has been able to develop." That line shows how a theory can give a deep reason for many facts. A law can be as simple as the rule that water boils at 100 degrees Celsius at sea level. That rule tells exactly what temperature the water will reach when it turns to steam, as long as the air pressure is normal. It does not say why water does that. The why is part of a theory about heat and molecules. The theory of heat explains that water molecules move faster when they get warm, and at a certain speed they can break away from each other and become vapor. The law is a reliable description. The theory is the story behind the description. A theory can be as familiar as the idea that birds migrate seasonally. The observation is that many birds travel north in spring and south in fall. The theory of migration says that birds do this to find food and safe places to raise young. The theory also predicts that if climate changes, the timing of migration may shift. That prediction can be tested by watching birds over many years. Some people argue that laws are only descriptions, not explanations. They say a law is just a pattern that scientists have noticed, like a rule that a ball falls faster if it is heavier. They claim the law does not tell why the ball falls faster. In that view, a law is like a note that says, "This happens," but does not answer the question, how does it happen? The argument is not wrong, but it misses the point that a law is meant to be a stable, simple statement that can be used over and over. The why is left to a theory. The two work together. The law gives a clear, testable fact. The theory builds a story that fits that fact and many others. Another common objection is that theories are just guesses. Some people think a scientist writes a theory and then hopes it will be right. They compare a theory to a wild guess that may or may not match reality. That view forgets that a theory must be tested. A theory that does not match observations is changed or abandoned. For example, before Darwin, many scientists guessed that species were fixed and could not change. Those guesses did not fit the many new fossils and animal observations that were being found. Darwin's theory of evolution survived because it explained many facts at once and made new predictions that were later confirmed. So a theory is more than a guess. It is a tested explanation. The acceptance of Newton's law of gravity shows how a law can become trusted. When Newton first published his law, many people were skeptical. The idea that an invisible force could act across empty space seemed odd. Yet a famous astronomer, Edmund Halley, asked Newton to explain why planets move in ellipses. Newton answered with his law and showed that the same rule that makes an apple fall also makes the moon circle the Earth. Over time, more and more observations matched the law. The law of gravity helped predict the return of a comet that had been lost for many years. When the comet reappeared exactly where Newton's calculations said it would, people began to trust the law. That story shows how a law can move from a new idea to a reliable tool. The early resistance to Darwin's evolution also tells a lesson. When Darwin published On the Origin of Species, many readers found the idea uncomfortable. Some religious leaders said that the theory went against the belief that all life was created in its present form. Some scientists argued that the fossil record did not show enough change. Darwin himself wrote, I have no doubt that the law of natural selection will be considered a principle of great importance. The debate lasted for decades, as more evidence piled up, such as the discovery of genetic inheritance and the finding of transitional fossils. The theory grew stronger. Today, evolution is taught in schools worldwide as a central scientific theory. The story shows that a theory can face strong opposition, but if it continues to match new evidence, it can become a cornerstone of knowledge. Real-world applications of laws and theories are everywhere. Engineers use the law that water boils at 100 degrees Celsius to design steam engines and cooking appliances. They rely on the law to know exactly when water will turn to steam, which powers turbines that generate electricity. The theory of heat tells them how to improve efficiency by reducing waste. In biology, the theory of evolution helps doctors understand why some bacteria become resistant to antibiotics. By seeing evolution as a process of natural selection, doctors can design treatment plans that slow down resistance. The theory also guides conservationists in protecting species that migrate. Knowing why birds migrate helps create safe stopover habitats. Modern scientists still talk about the difference between law and theory. Some say the line is blurry. In physics, the law of conservation of energy says that energy cannot be created or destroyed. The theory of quantum mechanics explains how energy behaves at tiny scales. Both are needed to describe what happens in a particle accelerator. In biology, the law of Mendelian inheritance describes how traits pass from parents to children. The theory of genetics explains the DNA code that makes those traits possible. The two work together, each filling a role. An analogy can help picture the relationship. Think of a law as a road map that shows where a city is located. The map tells the exact distance and direction. A theory is like the guidebook that tells why the city grew where it is, what its history is, and what you can expect to see there. The map is reliable for navigation. The guidebook gives depth and meaning. Both are useful, but they serve different purposes. Another analogy uses a recipe. A law is the list of ingredients and the exact measurements. It tells you that you need 2 cups of flour, 1 cup of water, and a pinch of salt. The theory is the explanation of why those ingredients combine to make bread. It tells how heat changes the dough, how yeast makes bubbles, and why the texture changes. The recipe works even if you do not understand the chemistry, but the theory helps you improve the recipe or create new ones. The difference also matters when scientists talk about laws breaking. Some people claim that when a law is broken, science is wrong. In reality, a law may only apply under certain conditions. The law that water boils at 100 degrees Celsius works at sea level. At high mountains, the air pressure is lower, so water boils at a lower temperature. The law still holds. The condition of pressure has changed. The theory of heat explains why the boiling point changes with pressure. So a law is not a universal command, it is a precise statement that works within its limits. In the same way, a theory can be refined. The theory of evolution began with natural selection. Later, scientists added ideas about genetic drift, gene flow, and molecular biology. Each addition made the theory richer, but the core idea remained. Living things change over time because of differences in survival and reproduction. The theory grew, but it never lost its status as a theory because it still explains many facts and makes new predictions. One more real-world example comes from weather forecasting. The law that warm air rises is simple and reliable. It tells meteorologists that warm air will move upward, creating low pressure. The theory of atmospheric dynamics explains how that rise interacts with wind, moisture, and the Earth's rotation to form storms. Using both the law and the theory, scientists can predict rain, hurricanes, and climate trends. The predictions help people plan travel, protect homes, and grow food. A final historical anecdote shows how a law can be challenged and then accepted. In the 1800s, many people believed that the motion of the planets could not be explained by a simple rule. They thought the heavens were perfect and unchanging. When Newton published his law of gravitation, it suggested that the same force that makes an apple fall also moves the planets. Some astronomers argued that the law could not handle the irregularities in planetary motion. Over time, more precise measurements showed that the law matched observations very well, except for a small discrepancy in Mercury's orbit. That tiny mismatch later led to Einstein's theory of relativity, which refined the law for very fast or very massive objects. The story shows that a law can be very strong, yet still open to improvement when new facts appear. In summary, a law is a concise statement of what happens under certain conditions. Theory is a broader explanation that tells why it happens and links many facts together. Newton's law of gravity and Darwin's theory of evolution illustrate the two roles. The boiling point of water and bird migration give everyday examples. Counterarguments remind that laws are descriptions and theories are not just guesses. Historical anecdotes about Newton's law gaining acceptance and Darwin's theory facing resistance show how ideas grow. Real-world uses in engineering, medicine, and weather show that both law and theory are tools for solving problems. Modern science keeps the two in dialogue, using simple laws and deep theories to build a clearer picture of the world. The analogies of maps, recipes, and roads help listeners see the partnership. By keeping the two separate yet connected, science builds a sturdy foundation for understanding. The idea that evidence can lift a claim or pull it down is as old as the habit of asking questions. In ancient markets, a merchant would test a piece of cloth by pulling it, and in the same way a thinker tests a theory by looking at the world. The modern study of how this works began in the 19th century, when scientists started to write down clear rules for what counted as proof. One of the first people to shape those rules was a philosopher named Karl Popper. Popper argued that a scientific idea must be able to be shown false. He called this the principle of falsification. In his own words, he wrote, "A theory is scientific only if it can be refuted by possible observations." The thought behind the quote is simple. If a claim cannot be tested at all, it does not belong in science. Popper's view grew out of a concern that many ideas were being protected from criticism by clever arguments. He saw the danger of letting a theory survive simply because no one could think of a way to break it. To avoid that, Popper said that scientists should try to find situations where a theory would fail. If they succeed, the theory must be changed or abandoned. If they fail, the theory survives for the time being, but it is never proved beyond doubt. This attitude makes science a never-ending search for better explanations, not a collection of final truths. A contrasting picture was offered by Thomas Kuhn, a historian of science who looked at how scientific fields actually changed over time. Kuhn described science as moving through periods of normal science, where researchers work within an accepted framework or paradigm, and then through revolutionary periods where that framework is replaced. He wrote, Science proceeds via a series of revolutions. In Kuhn's view, evidence does not always force a change in the same way Popper described. Sometimes scientists ignore evidence that does not fit the current paradigm, and only when enough anomalies pile up does a new paradigm appear. This picture shows that the path from evidence to theory can be messy. Both Popper and Kuhn agree that evidence matters, but they disagree on how it moves ideas. The disagreement can be seen in everyday examples. Imagine a new cleaning product that promises to remove tough stains. The maker says, if you spray this on a coffee spill, the stain will disappear. A test can be set up. A cloth with a fresh coffee spot is treated with the product, and the result is observed. If the stain remains, the claim is falsified. The product makers must then improve the formula or change the claim. This follows Popper's rule. A clear test could show the claim wrong. Now consider a weather forecast that predicts rain for the afternoon. The forecast is based on many measurements and models. When the afternoon passes, the sky is clear. The forecast is proven wrong. In a Popperian sense, the forecast is falsified, and the model that produced it must be adjusted. In a Kuhnian sense, forecasters might argue that the overall pattern of predictions is still useful, and a single miss does not overturn the whole system. They may point to other days when the model got it right, keeping the current paradigm alive. These simple stories illustrate how evidence can support or challenge ideas. They also show how the two philosophers would interpret the same event differently. Popper would focus on the single test that showed failure. Kuhn would look at the broader context and ask whether the failure is enough to cause a shift. The process of testing ideas does not happen in a vacuum. There are common objections that people raise when they think about evidence. One objection is the belief that any data can be twisted to fit a view. This view says that no matter what the numbers say, a clever person can spin the story to keep the original claim alive. Another objection is the claim that only positive results matter. In this view, scientists are praised when they find something that works, but failures are ignored or hidden. Both objections can weaken the link between evidence and belief. Popper addressed the first objection by insisting on clear, risky predictions. He wrote that a good theory must make statements that would be very unlikely if the theory were false. In that case, the data cannot be easily reinterpreted. Kuhn, on the other hand, pointed out that scientists are human and can be biased toward their current paradigm. He suggested that the community needs to be aware of these biases and be ready to change when enough evidence accumulates. The second objection, that only positive results matter, is known today as publication bias. It means that studies showing a new drug works are more likely to be printed than studies showing it does not. Popper would say that this bias blocks falsification, because the negative data never reaches the public. Kuhn would note that the scientific community may be stuck in a normal period where the dominant ideas are protected, and the bias helps keep the paradigm stable. Real-world applications of falsification and paradigm change are everywhere. In medicine, a new drug is tested against a placebo. If patients do not improve, the drug's claim is falsified and the company must revise its approach. In engineering, a bridge design is checked against stress tests. If the bridge fails under a certain load, the design is rejected. In both cases, the test is a clear way to see if the claim can survive. Modern interpretations of Popper's ideas have added new tools. Computer simulations now allow scientists to run many virtual experiments quickly. When a model predicts that a certain climate pattern will happen, The prediction can be checked against real climate data. If the data diverges, the model is falsified and must be refined. Some philosophers argue that with big data, falsification becomes harder because a model can be adjusted in many small ways to fit new data. They suggest that a new version of falsification should focus on the overall simplicity of a model, not just on single failures. Kuhn's view has also been updated. Some scholars talk about paradigm families where related ideas shift together. In technology, the shift from desktop computers to smartphones can be seen as a paradigm change. The old paradigm of typing on a keyboard and using a mouse gave way to touch screens and apps. The evidence that drove this change included user preferences, battery life, and the ability to connect to the internet anywhere. The transition was not smooth. Many companies tried to hold on to the old model, but the new evidence kept building. Analogies help to make these abstract ideas clearer. Think of a detective looking for a thief. The detective gathers clues, and each clue can either support a suspect or rule them out. If a clue shows that the suspect could not have been at the scene, the detective must look for another suspect. This is like falsification. A clue that does not fit the theory forces a change. In another analogy, imagine a gardener who plants a new type of seed. The gardener watches the seed sprout, grow, and bear fruit. If the seed never sprouts, the gardener knows the seed is not viable and must try a different one. The garden is the scientific field, the seed is the theory, and the observation of sprouting is the evidence. Historical anecdotes give weight to the discussion. In 1887, Albert A. Michelson and Edward W. Morley set up an experiment to detect the Earth's motion through the aether, a substance thought to fill space. Their equipment was designed to show a tiny shift in light speed if the ether existed. The result was a null finding. No shift was observed. This outcome falsified the ether hypothesis and opened the way for Einstein's theory of relativity. The experiment is a classic case of a clean test that could have shown the idea wrong, and it did. Another story comes from the early days of germ theory. In the 1860s, Louis Pasteur performed a series of experiments with broth in flasks. He showed that when the broth was boiled and then sealed, no microbes appeared, but when the flask was left open, microbes grew. This evidence contradicted the prevailing belief that spontaneous generation created life from non-living matter. Pasteur's work falsified the old idea and helped establish the modern view that germs cause disease. The story shows how a simple test can overturn a long-held belief. Both anecdotes illustrate the power of a well-designed experiment to challenge a theory. They also show how the scientific community reacts. After Michelson-Morley, many physicists tried to rescue the ether idea, but the weight of the evidence eventually led to a new paradigm. After Pasteur, some physicians clung to spontaneous generation, but the clear results forced a shift in medical practice. Quotes from the thinkers themselves add flavor. Popper wrote, "Science must be falsifiable, otherwise it is not science." Kuhn said, "A paradigm shift is a fundamental change in the basic concepts and experimental practices of a scientific discipline." These short lines capture the core of each view. In the everyday example of a cleaning product, a company may run a test where a stain is treated with the product and then measured for remaining color. If the color drops below a set threshold, the claim is supported. If not, the claim fails. The company can then either improve the formula or change the marketing. The same pattern appears in the weather forecast example. Forecast that predicts rain is checked against actual rain. If the forecast is wrong, The model that produced it is adjusted. The adjustment may involve adding more data, changing the algorithm, or even adopting a new way to think about atmospheric patterns. These stories also reveal how counter-arguments can appear. Some marketers might argue that a single failed test does not mean the product is bad. They may point to other tests where it succeeded. This mirrors Kuhn's idea that a single anomaly does not overturn a paradigm. Yet Popper would remind that each test must be able to show failure, and if many tests succeed, confidence grows. The tension between single-case focus and broader pattern is a recurring theme. The claim that only positive results matter shows up in the cleaning product world when companies only publish the best results. This creates a biased view of how well the product works. In science, similar bias can hide important failures. Popper warned that hiding failures blocks the self-correcting nature of science. Kuhn noted that the community's standards for what counts as a good result can keep a paradigm alive even when evidence mounts against it. Modern science tries to reduce these problems. Registries for clinical trials require that all outcomes be reported, whether they are positive or negative. In climate science, data sets are made public so that anyone can check the predictions. These practices aim to keep the link between evidence and theory strong, as Popper would like, and to make sure that the community can see when a paradigm needs change, as Kuhn would want. The idea of falsification also appears in legal reasoning. A lawyer presents evidence to prove a claim, but the defense looks for evidence that could falsify it. The courtroom becomes a place where claims are tested against reality. The same logic works in science. A claim stays alive only as long as no evidence has shown it false. In the digital age, algorithms that recommend videos or news articles are built on data. If the algorithm predicts that a user will like a video and the user does not watch it, that is a falsification of the prediction. Engineers can then adjust the algorithm. This shows that even everyday technology follows the same pattern of making predictions, testing them, and revising them. Some critics argue that because scientists can always add new variables to a model, no model can ever be truly falsified. They say that any failure can be blamed on a hidden factor. Popper responded that a theory should not be protected by ad hoc fixes. A good theory makes bold predictions that would be hard to save by adding extra clauses. Kuhn added that the community's shared standards help decide when a fix is reasonable and when it is just a way to keep the old paradigm alive. The scientific reasoning moves step by step, like a person who puts together a jigsaw puzzle. First, the person looks at the picture on the box, then tries a piece, and if it does not fit, the piece is set aside. In the same way, a scientist looks at a problem, makes a guess, tests it, and if the test fails, the guess is dropped. The whole process is built on logic, the set of rules that tell which thoughts follow from which other thoughts. John Stuart Mill was one of the first people to write down a clear list of logical steps for science. In his book, A System of Logic, he gave what are now called Mill's methods. The simplest of these is the method of agreement. Mill wrote, "When several instances of a phenomenon have only one circumstance in common, that circumstance is the cause of the phenomenon." In a chemistry lab, this meant that if a reaction happened every time a certain metal was present, the metal was likely the cause. One famous story tells how Mill's method helped a chemist discover that chlorine was needed to turn sodium into salt. The chemist mixed many substances, noted which ones produced a salty taste, and saw that only the mixtures containing chlorine gave the result. By agreeing on the common factor, the chemist isolated the cause. Charles Sanders Peirce added another piece to the logical puzzle. He called his approach abduction, which is a fancy word for making a guess that could explain the facts. Peirce said, "The purpose of a hypothesis is to be falsified." After a guess is made, Peirce argued that it must be tested by deduction, that is, by drawing out what should happen if the guess is true, and then by experiment. If the experiment shows something different, the guess is rejected. Peirce used this method when he worked on the problem of how light bends when it passes through a prism. He guessed that light consisted of tiny particles that changed direction. Then he calculated the pattern that should appear on a screen, and finally he ran the experiment. The pattern matched his calculation, so the hypothesis survived the test. The steps that Mill and Peirce described are not just old ideas. They are the same steps that a modern scientist follows when solving a puzzle about climate change. First, the scientist gathers data about temperature, greenhouse gases, and ice melt. Then the scientist forms a hypothesis, such as more carbon dioxide makes the planet warmer. Next, the scientist works out what other measurements should look like if the hypothesis is right, for example, higher ocean heat content. Finally, the scientist checks the real measurements. If the measurements line up, the hypothesis gains strength. If not, the scientist looks for a new guess. A second everyday example is finding the best route on a map. Imagine a driver who wants to go from town A to town B. The driver lists possible roads, checks which ones have traffic, and eliminates the ones that are blocked. The driver then picks the road that seems shortest and tests the choice by driving a short distance. If the road turns out to be slower than expected, the driver drops it and tries another. This is exactly the same logical pattern that science uses. List possibilities, rule out the wrong ones, pick the best, test, and adjust. Even with clear steps, some people argue that logic is not enough for science. One common claim is that emotions often overrule reason. The argument goes like this. A researcher who loves a particular theory may ignore data that contradicts it because the idea feels right. This is called motivated reasoning. Critics say that when emotions are strong, the logical steps can be skipped or twisted. To answer this, scientists have built safeguards. Peer review, for instance, asks other people to look at the work and point out any hidden bias. Double-blind experiments hide the identity of the treatment from both the participants and the researchers, so that personal feelings cannot sway the results. These tools keep the logical process alive, even when emotions try to creep in. A second counterargument says that some problems are so tangled that no clear step-by-step method can work. The claim is that in fields like economics or ecology, there are too many variables, so a simple hypothesis cannot capture the whole picture. Some philosophers reply that even in complex systems, logical reasoning still helps. They suggest breaking the big problem into smaller pieces, applying the same steps to each piece, and then seeing how the pieces fit together. This is called reductionism. While reductionism does not solve every difficulty, it shows that logic can still guide work on messy problems. Historical anecdotes show how the logical methods of Mill and Peirce were used in real discoveries. In the 1840s, a chemist named William Prout tried to understand why some acids tasted sour while others tasted bitter. He used Mill's method of difference. He compared two acids that were almost the same, except for one component. He found that the component that made the acid sour was hydrogen. By focusing on the single differing factor, Prout isolated the cause of sour taste. This work helped build the modern idea of acids and bases. Another story comes from Peirce's time at Johns Hopkins University. Peirce was asked to help design an experiment to test the hypothesis that a certain type of bacteria could break down iron in water. He wrote down the logical steps. First, assume the bacteria can do the job. Second, predict that water with the bacteria will lose its iron content faster than water without. Third, set up two identical tanks, add the bacteria to one, keep the other sterile. Fourth, measure iron levels over time. When the measurements showed a clear drop in the tank with bacteria, the hypothesis was supported. Peirce's careful use of hypothesis, deduction, and experiment became a model for many later scientists. The logical steps can also be seen in everyday decisions that are not about science. For example, a parent deciding which bedtime story to read may list the children's favorite characters, eliminate books that are too long, pick the one that matches the mood, and then see if the children stay calm. If the children become restless, the parent changes the choice next night. The same pattern of listing options, removing the bad ones, choosing the best, testing, and adjusting is at work. This shows that logic is a tool the mind uses in many areas of life, not just in laboratories. Quotes from the original thinkers help keep the ideas clear. Mill wrote, "The only way of arriving at the truth is through the method of induction." Induction means looking at many specific cases and finding a rule that fits them all. Peirce said, "We must not be afraid to be wrong." This reminder tells scientists that making a guess that can be proved false is a good thing, because it moves knowledge forward. When the steps are followed well, science builds reliable knowledge. The logical chain links observation, guess, prediction, and test. Each link can be checked by others, so the whole chain stays strong. If any link is weak, the whole argument can fall apart. That is why scientists pay close attention to each step. Sometimes the steps are hidden behind technical language, but the core idea stays the same. For instance, the phrase falsifiability sounds fancy, but it simply means that a hypothesis must be able to be shown false by an experiment. If a claim cannot be tested at all, it does not belong in science. This idea comes from Peirce and was later popularized by Karl Popper. The rule keeps science honest and keeps the logical process clear. Logical reasoning also helps scientists avoid the trap of confirmation bias, which is the habit of looking only for evidence that supports a belief and ignoring evidence that does not. By using Mills's method of residues, a scientist can ask, what part of the phenomenon is still unexplained after all known causes are taken into account? This question pushes the researcher to search for new explanations instead of staying with the familiar ones. Another practical tool is the use of control groups. In a medical trial, one group receives the new drug, another receives a placebo. The logical step is to compare the two groups to see if the drug makes a real difference. If the drug works, the results will differ in a predictable way. If not, the results will be similar, and the hypothesis that the drug helps will be rejected. This simple comparison follows the same logical pattern of hypothesis, prediction, and test. The map analogy can be extended further. Imagine a traveler who wants to reach a mountain peak. The traveler looks at a topographic map, marks possible paths, checks which paths avoid steep cliffs, and then chooses the safest route. Along the way, the traveler watches the terrain and may change direction if a new obstacle appears. This constant checking and adjusting mirrors the scientific method. The traveler does not claim to know the exact future, but uses logical steps to stay on track. In modern times, computers help apply logical steps faster. Machine learning algorithms test thousands of hypotheses at once, but they still follow the same pattern. Propose a model, calculate what the model predicts, compare predictions to data, keep the models that work best, discard the rest. Even though the process is automated, the underlying logic is unchanged. Some critics argue that computers remove the human element of judgment, and that logic alone cannot capture the creativity needed for breakthroughs. The response is that logic provides the scaffolding, while creativity supplies the new guesses to test. Without the scaffolding, the guesses would float without direction. The partnership of logic and imagination is what drives scientific progress. The story of the discovery of the structure of DNA shows this partnership. Watson and Crick used logical steps to piece together clues from X-ray photographs, chemical data, and known chemistry of nucleic acids. They eliminated models that could not fit the data, such as a triple helix model, and kept the double helix model that matched all observations. Their logical elimination of wrong pieces was like solving a puzzle by discarding pieces that did not fit the picture. In another field, astronomers use logic to find exoplanets. They look at the light from a star, notice a tiny dip when a planet passes in front, and then calculate the planet's size and orbit. If the dip repeats at regular intervals, the hypothesis that a planet is causing it gains strength. If the dip is irregular, the hypothesis is rejected. The logical steps turn tiny changes in light into a whole new world. The logical method also helps in everyday policy making. When a city wants to reduce traffic accidents, it may collect data on where crashes happen, form a hypothesis that better street lighting reduces crashes, predict that adding lights will lower numbers, install lights in a test area, and then compare crash rates before and after. If the numbers drop, the hypothesis is supported. If not, the city looks for another cause. This mirrors the scientific process and shows how logic guides practical decisions. To keep the logical chain strong, scientists write down each step in detail. This practice is called transparent reporting. It allows the story of science is not just about lonely geniuses in quiet labs. It is also a story about groups, cultures, and the money that helps ideas grow. The idea that science is a social activity goes back many years. One of the first people to write about it was Robert K. Merton. In the 1940s, Merton said that science works like a set of rules that people follow. He called those rules norms. One of the norms is communalism, the idea that knowledge belongs to everyone. Merton wrote, "The product of scientific work is a public good that belongs to the community." This simple line tells us that science is meant to be shared, not kept secret. Merton's view was shaped by the world he lived in. After World War I, many scientists saw how teamwork could change the course of history. The Manhattan Project is a clear example. In the early 1940s, a group of physicists, engineers, and technicians gathered in secret locations across the United States. They were asked to build a new kind of weapon before the war ended. No single person could have done the job alone. The project needed mathematicians to solve equations, chemists to handle materials, and machinists to build parts. The success of the project showed that large groups can solve problems that are too big for individuals. It also showed that the social side of science can have powerful, sometimes dangerous, results. Another early example of collaboration comes from the Royal Society in England. In 1660, a group of curious men gathered in a coffee house and decided to start a club. They wanted to share experiments, discuss ideas, and publish what they learned. The society's first meetings were simple. Members would bring a small experiment and talk about it over tea. Over time, the society grew into a formal institution that published the first scientific journal, Philosophical Transactions. The early members believed that sharing results would speed up discovery. Their story shows that even in the 1600s, people understood that science needs a community. Today, the idea that science is social still matters. Modern science journalists often write about how research teams work together. A journalist named Ed Yong, for example, has described how a team of virologists shared data during the COVID-19 pandemic. He wrote that the speed of the response depended on scientists sending each other results, samples, and ideas across the world. This shows that the social side of science is not just a historical footnote. It is a daily reality. The social side of science can be seen in everyday life. Think about a school science fair. A student rarely works alone. The student asks a teacher for help, a parent for supplies, and friends for ideas. The final project is the result of many small contributions. If the student tried to do everything alone, the project might be smaller or less polished. The same pattern appears in community gardens. Neighbors share seeds, knowledge about soil, and tools. One person may know how to compost. Another may know which plants attract bees. The garden thrives because people exchange what they know. These simple scenes mirror the larger world of scientific research. One analogy helps to picture the social side of science. Imagine a kitchen where a dinner is being prepared. Chef cannot make a 5-course meal alone. The chef needs a sous chef to chop vegetables, a baker to make bread, and a server to bring dishes to the table. Each person adds a skill, and the whole meal is better than any single dish. Science works in a similar way. Researchers bring different skills, and together they create knowledge that is richer than any single mind could produce. There are arguments that push back against the idea that science is mainly social. The first counter-argument says that great discoveries come from solitary thinkers. People point to stories of Isaac Newton working alone in his garden or Albert Einstein writing his papers in a quiet office. They claim that the best ideas need quiet, personal thought, not the noise of a group. The second counter-argument says that money always guarantees truth. Some believe that if a study is funded by a big agency, the results must be correct. They think that money can protect research from error. Both counter-arguments miss important points. The story of Newton is often told as if he worked in complete isolation, but even he exchanged letters with other scientists, such as Robert Hooke and Edmund Halley. Those letters helped him test his ideas about gravity. Einstein also relied on discussions with friends like Michele Besso and the work of others to shape his theory of relativity. Even the most famous lone geniuses needed a network of peers. The claim that money always guarantees truth also falls short. Funding can help a project get equipment and staff, but it does not make the results automatically right. Sometimes money can create pressure to produce certain outcomes. A well-known example is the case of the drug Vioxx. The company that funded the research pushed for quick approval, and later the drug was found to cause heart attacks. The failure showed that money can sometimes hide problems instead of fixing them. Real-world applications of the social side of science are everywhere. Climate research, for instance, depends on a global network of scientists who share data from satellites, ocean buoys, and weather stations. No single country could collect enough information to understand the whole system. The Intergovernmental Panel on Climate Change, IPCC, brings together hundreds of experts to write assessment reports. Those reports guide policy decisions around the world. The success of the IPCC rests on the belief that many minds working together can see patterns that a single researcher could miss. Another modern example is the development of the COVID-19 vaccines. Companies like Pfizer and BioNTech partnered with universities, government labs, and other firms. The partnership allowed them to combine knowledge about mRNA, manufacturing expertise, and regulatory experience. The result was a vaccine that was ready in less than a year, a speed that would have been impossible for any one group alone. The story shows how shared effort can turn a scientific breakthrough into a life-saving product. Science journalists today often talk about team science. They note that many grant agencies now require researchers to include a plan for collaboration. The National Institutes of Health, for example, asks for a team science section in grant proposals. The idea is that funding bodies recognize that big problems need many perspectives. This modern policy reflects Merton's norm of communalism, updated for the present day. The social side of science also includes culture. Different societies value different kinds of knowledge. In some cultures, knowledge from elders and local healers is respected. In other places, laboratory data is seen as the highest authority. When scientists work across cultures, they must learn to respect each other's ways of knowing. An example comes from the study of malaria in Africa. Researchers who partnered with local health workers learned that community trust was essential for distributing bed nets. The partnership led to higher usage rates than a top-down approach would have achieved. A second cultural example comes from the field of astronomy. Indigenous peoples around the world have long watched the night sky and built stories about the stars. Modern astronomers now collaborate with indigenous groups to protect dark sky sites that are important for both scientific observation and cultural heritage. By listening to each other, both science and culture benefit. There are also practical lessons from the social side of science that can help students. When a group works on a class project, it helps to assign clear roles. One student can gather data, another can write the report, and a third can create the presentation. By dividing tasks, the group can finish faster and produce a better final product. This mirrors how research labs assign experiments to different members. In a community garden, people often hold regular meetings to decide what to plant each season. They share what worked last year and what failed. Those meetings create a shared plan that uses the strengths of each gardener. The garden's success depends on that ongoing conversation. The same principle applies to scientific teams that hold weekly meetings to discuss results and plan next steps. A quote from Merton captures the spirit of these ideas. He wrote, "Science is a collective enterprise that thrives on openness and shared responsibility." The line reminds listeners that the heart of science beats in many hands. Another quote comes from the physicist Richard Feynman, who once said, "Science is a way of trying not to fool yourself." Feynman added that this effort is easier when many eyes check each other's work. The quote highlights how collaboration can keep science honest. The social side of science also means that mistakes can be caught early. In a large team, one member may notice an error that another missed. Peer review, the process where other scientists read a paper before it is published, is a formal version of this safety net. The system is not perfect, but it shows how the community helps keep knowledge reliable. Sometimes the social side can also slow progress. Large groups may need to reach consensus, which can take time. In the early days of the Human Genome Project, Scientists debated how much data to release publicly. Some argued for keeping data private until they could publish first. Others pushed for open sharing. The decision to release data openly helped accelerate research worldwide, but the debate showed that social dynamics can create tension. The role of funding adds another layer to the social picture. Funding agencies often set priorities that shape what gets studied. If a government decides to spend more on renewable energy, many labs will shift toward that topic. This can be good because it directs resources to pressing problems. However, it can also mean that less popular fields receive less support. The balance between societal needs and scientific curiosity is a constant conversation. A modern interpretation of Merton's ideas comes from the field of open science. Open science encourages researchers to share data, code, and methods openly online. Platforms like GitHub let scientists post their software so anyone can use or improve it. This practice turns the communal norm into a digital habit. It also helps people in low-resource settings access the same tools as those in wealthy labs. Open science also connects to the idea of citizen science. In citizen science projects, members of the public help collect data. An example is the Galaxy Zoo project, where volunteers classify images of galaxies. The volunteers' work helped astronomers sort millions of pictures much faster than a small team could. This shows that the social side of science can reach far beyond professional labs. The social side of science is not just about collaboration. It is also about responsibility. When a scientific finding influences public policy, the whole community must consider the impact. The case of leaded gasoline illustrates this. In the 1920s, scientists discovered that adding lead to gasoline improved engine performance. The auto industry promoted the idea, and many governments allowed its use. Later, research showed that lead caused severe health problems. The scientific community, together with public health officials, eventually pushed for bans. The story shows how social forces can both spread and later correct harmful practices. Another responsibility appears in the field of artificial intelligence. Researchers often work in teams that include ethicists, lawyers, and social scientists. The goal is to anticipate how new technology might affect jobs, privacy, and fairness. By involving many voices, the team hopes to create tools that benefit society rather than cause harm. In summary, the social side of science touches every part of the process. From the early meetings of the Royal Society to the massive collaborations of the Manhattan Project, from school projects to community gardens, from funding agencies to open science platforms, the pattern repeats. Knowledge grows best when people share, discuss, and check each other's work. The arguments that science is only an individual pursuit or that money always guarantees truth miss the larger picture. Real examples show that teamwork, culture, and careful funding all shape what science becomes. The final thought rests on a simple truth. Science is a human activity. Humans live in groups, speak languages, and need resources. When scientists remember that they are part of a larger community, they can build knowledge that is stronger, more reliable, and more useful for everyone. The words of Merton, "Science is a collective enterprise," remain a guide for anyone who wishes to understand how the world learns. Science and ethics have walked side by side since the first time a human tried to change the world with a tool. The question of what a scientist may do and what a scientist must do has always been part of the story of knowledge. Long before the word ethics was used in a lab, People asked whether a new medicine should be given to a whole village or only to a few. Those early questions form the roots of today's debate about limits and responsibilities. The modern study of ethics in science began to take shape in the 20th century. One early voice was that of Hans Jonas, a German philosopher who survived the Holocaust and later taught in the United States. Jonas wrote that modern technology gives humans power that was once only the domain of gods. He warned that such power creates a new kind of responsibility. In his book, The Imperative of Responsibility, he wrote, "We are called upon to think the future as a moral horizon, not as a distant unknown." Jonas argued that the ability to alter life itself means that scientists must ask what future they are creating, not just what they can create. Jonas was not alone. After World War I, the Nuremberg trials revealed how scientific research could be turned into a tool of cruelty. The trials produced the Nuremberg Code, a set of rules that said any experiment on a human being must be voluntary and must avoid unnecessary harm. The code gave a clear example of how law and ethics can shape scientific practice. It also showed that when science is left unchecked, the results can be terrible. In the decades that followed, many bioethicists built on these ideas. Peter Singer, for example, applied a utilitarian view, looking at the greatest good for the greatest number, to medical decisions. He asked whether it is right to allocate a scarce organ to a young patient rather than an older one. Another modern voice is the group known as the International Bioethics Committee, which advises the World Health Organization on how to handle new health technologies. Their statements often stress that respect for human dignity must guide scientific work. These thinkers have offered arguments that shape the current conversation. One core argument says that science cannot be free of moral limits because its outcomes affect real lives. When a researcher creates a new drug, that drug will be taken by patients, by children, by the elderly. The scientist therefore has a duty to consider safety, fairness, and access. Jonas summed this up by saying that the power to change life demands a duty to protect life. The argument also points out that without ethical guidance, science may produce tools that widen inequality or cause environmental damage. A second argument focuses on the idea of precaution. This view holds that when a new technology could cause irreversible harm, scientists should pause and test the risks before moving ahead. The precautionary principle is often used in debates about climate engineering or gene editing. It asks whether it is wise to launch a powerful tool when the full impact is still unknown. The principle does not stop progress, but it asks for careful steps that protect future generations. Both arguments have strong supporters, but there are also clear counterarguments. One counterargument claims that science should never be limited by moral concerns. Proponents of this view argue that any restriction slows the search for truth and the development of useful inventions. They point to historical moments when fear held back progress, such as when early researchers were blocked from studying electricity because it was thought to be dangerous. They say that if scientists are forced to ask, "Is this ethical?" before each experiment, the pace of discovery will grind to a halt. A second counterargument says that ethics often serve as a tool for special interests to block change. Critics claim that powerful corporations or governments may hide behind moral language to keep new technologies out of the market, protecting their own profits or control. In the case of certain medical trials, some argue that ethical review boards have delayed life-saving drugs from reaching patients in poor countries. The claim is that ethics can be used to slow progress rather than to guide it wisely. These counterarguments are not without merit, and they push the conversation forward. The challenge is to find a balance that respects both the drive to explore and the need to protect. Real-world examples help illustrate how this balance plays out in everyday life. Consider the case of a person who receives a home health test that can detect a serious disease early. The test is accurate, but the result is private. The person must decide whether to share the result with family, with an employer, or with a health insurance company. If the result is shared, it could lead to early treatment and possibly save a life. However, it could also lead to discrimination, higher insurance premiums, or unwanted stress for relatives. This dilemma shows how scientific information carries ethical weight. The person's decision reflects the broader question of how much personal data should be open to others. A second everyday example involves a new smartphone app that tracks a user's location to suggest nearby restaurants. The app promises convenience, but it also collects precise movement data. The user must decide whether to allow the app to keep this data, knowing that it could be sold to advertisers or used by law enforcement. If the data is shared, the user enjoys personalized offers and possibly safer navigation. If the data is kept private, the user retains control over their movements, but may miss out on benefits. This scenario mirrors larger debates about surveillance, consent, and the trade-off between utility and privacy. Analogies can make these ideas clearer. Imagine a child with a powerful new toy that can build anything out of blocks. The child can create a beautiful castle, but also a wall that blocks a doorway. If the child is left alone without guidance, the wall might trap the child's own toy figures. A parent who watches the child can step in to suggest building doors as well as walls. Science is like the child's toy, and ethics is like the parent's gentle guidance. The goal is not to stop the child from playing, but to help shape the play so that it brings joy rather than harm. Another analogy compares science to a river. The river carries water that can irrigate fields, generate power, and support life. Yet the same river can flood a town, erode soil, and spread disease if left unchecked. Building levees and channels does not stop the river. It directs the river's flow towards safe uses. Ethics works like those levees, shaping the flow of scientific power so that it benefits society without causing disaster. Historical anecdotes bring these ideas to life. One famous story is the Tuskegee syphilis study, which began in 1932 in the United States. The study followed a group of African American men who had syphilis, but the researchers did not tell the men they were sick, nor did they offer treatment, even after penicillin became widely available. The study continued for 40 years, causing needless suffering and death. When the public learned of the study in the 1970s, there was outrage. The episode led to the creation of the National Research Act and the establishment of institutional review boards, IRBs. IRBs are committees that review research proposals to ensure they meet ethical standards, such as informed consent and risk minimization. The Tuskegee case shows how a lack of ethical oversight can damage trust and cause lasting harm. A more recent anecdote involves the rise of CRISPR gene editing technology. In 2015, scientists announced that CRISPR could cut DNA with unprecedented precision. The promise was huge. The ability to fix genetic diseases, improve crops, and even bring back extinct species. But the power also raised alarm. In 2018, a Chinese scientist announced the birth of twin girls whose genes had been edited to be resistant to HIV. The announcement sparked a global outcry. Many scientists argued that the editing was done without proper consent, without long-term safety data, and without public discussion. The International Summit on Human Gene Editing later declared that heritable gene editing should not proceed until safety, efficacy, and societal consensus are achieved. The CRISP debate illustrates how modern science can move faster than the rules meant to guide it, and why continuous ethical dialogue is essential. Modern interpretations of the science-ethics relationship build on these stories. Some scholars propose a responsible innovation framework. This view asks scientists to anticipate possible impacts, involve the public early, and be willing to change direction if concerns arise. The framework is used in fields like nanotechnology and artificial intelligence. In AI, for instance, developers are urged to embed fairness, transparency, and accountability into algorithms before they are released. The idea is that responsibility is not an afterthought, but a part of the design process. Another contemporary approach is ethical by design. This concept suggests that ethical considerations should be built into the hardware and software from the start. In the case of the location tracking app, designers might include settings that let users delete their data automatically after a short period. In medical testing, companies might create secure portals that let patients control who sees their results. By embedding choice and protection into the product, the burden on the individual is reduced, and the technology becomes safer by default. Quotes from primary sources help keep the discussion grounded. Jonas wrote, "The future is not a gift, but a responsibility." The Nuremberg Code states, "The voluntary consent of the human subject is absolutely essential." The Belmont Report, another foundational document, declares, "Respect for persons, beneficence, and justice are the basic ethical principles." These words echo across decades, reminding that the core ideas remain the same even as the tools change. The debate over limits also appears in the field of environmental science. Climate researchers often face pressure to publish results quickly to warn the public. Some argue that releasing incomplete data could cause panic or economic loss. Others say that any delay could cost lives as the planet warms. The ethical question here is whether the urgency of the problem outweighs the need for scientific certainty. Many scientists now practice open science, sharing data as soon as possible while clearly noting uncertainties. This practice tries to meet both the demand for speed and the demand for accuracy. In the realm of biotechnology, the question of designer babies shows how ethics can shape policy. If parents could choose eye color, height, or intelligence for their children, society would have to decide whether such choices are fair, whether they could increase inequality, and whether they respect the child's autonomy. Some ethicists argue that allowing such choices treats children as products, not as persons. Others argue that parents already make many choices about their children's health and education, and gene editing is just another tool. The conversation continues in public hearings, academic journals, and social media. The role of ethics in science also touches on the distribution of benefits. The COVID-19 pandemic highlighted how vaccines were developed at record speed. The scientific community celebrated the achievement, but critics pointed out that low-income countries received vaccines later than richer nations. The ethical issue is not about the science itself, but about how the fruits of science are shared. Global initiatives like COVAX aim to address this gap, showing that ethical considerations can lead to concrete policies that improve equity. Another practical example is the use of animal testing. Scientists argue that animal models are essential for understanding disease and testing safety. Animal rights activists counter that causing pain to sentient beings is morally wrong, and that alternative methods, such as organ-on-a-chip technology, should replace animal work. The debate has led to regulations that require researchers to use the least harmful methods possible and to justify the need for animal subjects. This compromise reflects a balance between scientific necessity and moral concern. The conversation about limits also includes the idea of dual-use research. Some scientific work can be used for good or for harm. For example, research on viruses can help create vaccines, but the same knowledge could be misused to create bioweapons. The 1975 Asilomar Conference on recombinant DNA set a precedent. Scientists voluntarily agreed to pause certain experiments until safety guidelines were in place. This historic self-regulation shows that the scientific community can act responsibly without waiting for external laws. Modern bioethicists often use case studies to teach these concepts. A common case involves a researcher who discovers a gene that makes a certain type of cancer more aggressive. The researcher could publish the finding immediately, alerting doctors and patients, but the data also reveals a potential target for a harmful weapon. The ethical dilemma is whether to publish fully, to redact details, or to withhold the information altogether. Different ethicists propose different solutions, but all agree that the decision must weigh benefits against risks. The notion of social license is also relevant. It means that science must earn the trust of the public to operate freely. When trust is lost, as in the case of the Tuskegee study, the public may reject beneficial technologies. Restoring trust often requires transparency. The future of science feels like a quiet road that stretches far ahead. It is a road that many people travel every day without seeing the work that built it. In this part of the story, the focus is on the questions that still hang over the horizon. The story brings together the ideas of Naomi Oreskes, a historian of science, and a group of AI researchers who study how machines think. It also shows how a phone can show a temperature rise and how a smart speaker can answer a question about the stars. All of these pieces help to paint a picture of what science may look like tomorrow. Naomi Oreskes grew up watching the climate debate grow louder in the 1990s. She learned that the public often trusts a single study more than a whole field. She wrote, "Science is not a set of facts, but a process that builds trust." That sentence is a reminder that trust is the glue that holds scientific work together. Oreskes argues that the future of science depends on keeping that glue strong. She says that open data, open methods, and open review are the best ways to keep trust alive. In her view, the biggest challenge is not a lack of data, but a lack of confidence in how that data is used. At the same time, a new group of thinkers is looking at the rise of artificial intelligence. Some of them, like the researcher Fei-Fei Li, speak about human-centered AI. They say that AI should help people, not replace them. Others, such as the philosopher Nick Bostrom, warn that a super-intelligent machine could outthink any human. The clash between these two views creates a lively debate about the role of AI in future science. The debate is not just about computers. It is about how people will make sense of the world when machines can crunch numbers faster than any mind. One everyday example of this clash is the smart assistant on a phone. When a person asks, "What will the weather be tomorrow?" the assistant pulls data from a model that runs on a server far away. The answer arrives in seconds. The person does not see the equations, the code, or the data that the model used. The assistant hides the complexity behind a friendly voice. This small moment shows how science is becoming a service that people use without thinking about the work behind it. Another everyday example is the climate tracking app that shows a rise in average temperature over the past year. The app pulls data from satellites, weather stations, and ocean buoys. It then draws a simple line graph that anyone can read. The line goes up a little each year. The app does not ask the user to understand the math of radiative forcing or feedback loops. It simply shows a picture that says, "The planet is warming." In both cases, the user gets a result, but the question of how reliable the result is remains. The story of climate modeling in the 1970s offers a useful historical anecdote. In the early 1970s, a handful of scientists began to use the new digital computers to simulate how the atmosphere might change. One of those scientists, Syukuro Manebe, built a simple model that linked carbon dioxide levels to temperature. The model was crude, but it showed a steady rise in temperature when CO increased. At first, many people dismissed the model as too simple. Over time, the model was refined, data improved, and the basic idea held true. The rise of climate modeling shows how a small, uncertain step can become a cornerstone of modern science. A second anecdote comes from the early days of computer-based simulations of weather. In 1950, John von Neumann and his team ran the first numerical weather prediction on the ENIAC computer. They fed in temperature and pressure readings and let the computer calculate how the air would move. The forecast was not perfect, but it proved that a machine could do something that humans could not do by hand. That experiment opened the door to modern climate models, which now run on supercomputers and predict future climate with great detail. The anecdote shows that the tools of science can change the way questions are asked. The current debate about AI often includes a strong counterargument. That AI will replace all human reasoning. Some people say that once a machine can prove theorems, write poems, and diagnose diseases, there will be no need for human thought. They point to the rapid progress of deep learning and to machines that can beat champions at chess and Go. The argument sounds convincing because it rests on clear examples of machine success. A second counterargument comes from climate skeptics who claim that the data is too uncertain to act on. They say that because models differ, because measurements have error bars, and because the future is unknown, it is better to wait. They quote the phrase, "The science is not settled," as a reason to delay policy. This view suggests that acting on climate data could cause unnecessary economic harm. Both counterarguments have strengths, but they also have weaknesses. The AI replacement claim forgets that many scientific decisions involve values, ethics, and creativity. A machine can calculate a probability, but it cannot decide what is fair or what risk is acceptable. Human judgment remains essential in setting research goals, interpreting results, and deciding how to use new knowledge. The claim also ignores that AI systems need data that humans collect and label. Without people, the machines would have nothing to learn from. The climate uncertainty claim also leaves out key facts. While models do have error bars, they agree on the direction of change. The planet is warming, and human activity is a major driver. The Intergovernmental Panel on Climate Change, IPCC, reports that the range of possible warming is narrower than many think. Waiting for perfect certainty would mean waiting for the damage to become irreversible. The claim also ignores the cost of inaction, which can be measured in lives, property, and ecosystems. Real science already mixes these ideas. In medical research, AI helps find patterns in large datasets, but doctors still decide which treatment to give. In climate policy, governments use model projections to set emissions targets, while also listening to local communities about what changes are acceptable. The mix of machine help and human judgment is a pattern that may define the future. Modern interpretations of the future often use analogies to make the ideas clearer. One common analogy compares scientific progress to a garden. The seeds are ideas, the soil is data, and the gardener is the community that tends to both. A can be seen as a new kind of watering system that delivers water more evenly, but the gardener still decides which plants to grow. Climate data is like a weather forecast that tells the gardener when to plant or harvest. The gardener cannot ignore the forecast, even if it is not perfect, because the risk of a frost could ruin the crops. Another analogy treats scientific knowledge as a map. Early maps were rough sketches that showed only coastlines. Over time, explorers added more detail. A is like a satellite that can scan the whole Earth in minutes, adding new roads and landmarks. However, the map still needs a compass, a sense of purpose, and a traveler who decides where to go. The compass represents human values and goals. Without it, the map would be beautiful but directionless. The conversation about the future of science also includes voices from other fields. Philosopher of science Peter Lipton once said, "The best science is the one that can be trusted by the public." That sentence reminds readers that trust is not automatic. It must be earned through openness and honesty. Trust is also what Orestes calls the process that builds trust. The two sentences together show that trust is both a method and a goal. In the realm of AI, a researcher named Andrew Ng has often warned, "AI is the new electricity." He means that AI will become a basic tool that powers many parts of life, just as electricity does. The warning also hints that, like electricity, AI must be handled safely and fairly. The quote is simple, but it frames the whole debate about AI's role in science. The future also raises questions about who gets to shape the science that will affect everyone. Open data platforms, such as the Global Climate Observing System, let anyone download temperature records. Open source AI tools let anyone train a model on their own data. These platforms echo Orestes' call for openness. Yet, there are still barriers. Some datasets are behind paywalls, and some AI models are kept secret for commercial reasons. The tension between openness and profit is a fresh challenge for the coming years. One practical way to see the future in action is to look at how a smart assistant can help a student learn about photosynthesis. The student asks, "Why do plants need sunlight?" The assistant pulls from a database of biology texts and explains the process in simple terms. The assistant does not replace the teacher, but it gives the student a quick answer that can spark curiosity. The same pattern may appear in research labs, where AI suggests a new experiment based on past results, while the scientist decides whether the suggestion fits the larger goal. Another practical example is a farmer who uses a phone app to monitor soil moisture. The app shows a graph that updates every hour. The farmer can decide when to water the field, saving water and increasing yield. The data comes from sensors in the ground, processed by a cloud AI that predicts the best watering schedule. This example shows how scientific data, AI, and everyday decisions can blend together. Looking ahead, several open questions remain. First, how will societies decide which AI tools are safe to use in research? Will there be a global board that reviews AI models, similar to how drug agencies review new medicines? Second, how will climate scientists communicate uncertainty without causing paralysis? Will they adopt new visual tools that show risk in a more intuitive way? Third, how will education adapt to a world where AI can answer factual questions instantly? Will schools focus more on critical thinking and less on memorization? The answers are not yet clear, but the discussion is already moving forward. Conferences bring together orescas, AI ethicists, climate modelers, and policymakers. In those rooms, people argue, they listen, and they write new guidelines. The process mirrors the earlier story of climate modeling in the 1970s, when a few scientists argued for more data and better computers. Their persistence turned a tiny idea into a global effort. Another parallel can be drawn with the early computer simulations of the 1950s. Those pioneers faced skepticism that a machine could predict the weather. They kept testing, fixing bugs, and sharing results. Over time, the simulations became trusted tools. The same pattern may repeat with AI in science. Early doubts may give way to confidence as the tools improve and as people learn how to use them responsibly. The future of science also invites a simple question. What does it mean to know something? In the past, knowledge was often tied to a single expert who could explain a phenomenon. Today, knowledge is spread across networks of data, algorithms, and people. The shift does not erase the role of experts, but it changes how expertise is expressed. An expert may now be someone who can ask the right question of an AI system, rather than someone who can calculate every answer by hand. A quote from the physicist Richard Feynman helps to illustrate this shift. He said, "What I cannot create, I do not understand." In the age of AI, creating a model that can predict a climate pattern may be a way to show understanding. Yet, the model is only as good as the data and the assumptions fed into it. The quote reminds readers that building something is still a test of knowledge. The conversation also touches on ethics. If an AI system suggests a new drug that could save lives, who is responsible if the drug has side effects? The answer may involve shared responsibility between the developers, the researchers, and the regulators. This question mirrors the older debate about who owns scientific data. In the 1970s, climate modelers argued over whether their code should be public. Today, the same argument appears in AI, where some developers keep code secret to protect commercial interests. Finally, the story returns to the everyday person. When a person asks a smart assistant about the best route home, the assistant uses traffic data, weather data, and a map. The person trusts the answer because the system has worked before. That trust is built on a long line of small successes, just as trust in climate science is built on decades of measurements. The future will add more layers to that trust, but the basic idea stays the same. People rely on tools that have shown they work. In summary, the future of science is a mix of open questions, new tools, and old values. Thinkers like Naomi Oreskes remind us that openness and